Hey, my name is Daniel Velasco, and today I'm going to show you how math is quite literally in the air, specifically within the HVAC world. Now, whether we realize it or not, math plays a very big role within keeping the buildings that we live in and work in comfortable and energy efficient. From calculating airflow to also figuring out duct sizes, math is working behind the scenes every second. So let's dive within how these numbers help power the air that we breathe every single day. Now let's talk a little bit about me. My name is Daniel Velasco Jr. and I am currently a second-year student at Colorado Mine College. I am 20 years old and I have a deep interest in learning, especially when it comes to HVAC. It's one of those things that we often take for granted, but once we start working in the field, you realize how complex and fascinating it truly is. I chose this topic because HVAC isn't just something that I'm interested in. It's actually part of my daily life. I help run my family's business, which is called GMCH, and I serve as a CEO. Being part of this industry so early within my life has really opened my eyes to how important math-heavy HVAC work really is. Outside of work and also school, I'm always curious whether that's exploring new places and or learning something new. And as far for the info within this project, most of it comes from my dad, who's been in the industry for a couple years. He shared lessons from real-world experiences that go way beyond the classroom. For the interview portion of my project, I decided to sit down with someone that I have learned a lot from. His name is Daniel Velasco, the owner of GMCH, and yes, that is also my dad. We had a conversation on February 21st, 2025, right here in Gypsum, Colorado, and it lasted a few hours. It was an awesome experience to get his perspective, not just as a technician or a business owner, but also as someone who's seen the industry evolve over time. He shared the ups and also the downs that the job has to offer, the kind of mindset it takes to succeed, and how important math and problem solving is in the field. If you're curious about the company by any way, feel free to check out the website called gmch.us for more info on who we are and what we do. During the interview, my dad gave me a great look into what working in HVAC really is like. He told me the thing that he enjoys the most is how every day brings something completely different. It's all hands-on, and there's a real sense of accomplishment when fixing a problem or installing a system that helps people stay comfortable. Plus, HVAC is a steady career. There's always demand, which means that there's always work. That said, it's not without challenges. Colorado weather can be extreme, and sometimes troubleshooting problems takes a lot of trial and error. On top of that, the technology is consistently changing, so you're always learning something new. He broke down the skills needed for success, and physically, you've got to be strong and comfortable within tight and awkward spaces. Mentally, it takes focus and strong problem-solving skills, and emotionally, patience and communication are key, especially when things don't go as planned. We highly recommend trade schools, hands-on apprenticeships, and also learning electrical systems early on. Getting certified and gaining field experience as soon as possible also gives you a serious head start. His advice was to ask questions, never stop learning, and also take pride within your work. And one major thing he also came to emphasize was math. From figuring out airflow and calculating refrigerant levels, math is very essential. If you mess up the numbers, the system won't run right. Now let's dive a little more on how math plays a role within the HVAC world. Because of its involvement in almost every part of the job, HVAC stands for heating, ventilation, and also air conditioning within the systems that also helps to regulate indoor temperature, humidity, and the air quality. Basically, it's what keeps our homes and buildings livable and also comfortable all year round. Now, when we think about math within the field, we're not just talking about basic arithmetic. HVAC technicians also use algebra in order to calculate airflow and solve the unknown variables. Geometry comes to help with duct layout and also figuring out how air moves through different spaces. Trigonometry comes in when calculating angles or duct runs and piping. And even calculus can show up when working with advanced systems efficiency and or energy analysis. You may ask yourself, why does all of this matter? It matters because without the right math, systems could end up underpowered, oversized, or completely inefficient. And those mistakes aren't just costly, they can also impact people's comfort and safety. From what I have learned within my interview, it's clear that being good with tools is only part of the job. You have to think critically, solve problems fast, and also understand how math ties all the practices and pieces together. In HVAC, math isn't just helpful, it's a must. Now let's move forward with one of the most important parts of this whole project, the questions. Within this, there will be calculating main variables and also numerical information. I will provide the answers at the end, but feel free to give it a try. Now let's take a look at a world problem that involves HVAC refrigerant flow. Here we have a technician designing a refrigerant system. This system needs 500,000 BTU per hour of cooling capacity, and it uses R410A refrigerant. In order to ensure that everything runs smoothly, the technician must size the suction line correctly. In this case, the total equivalent length of the suction line is 50 feet, and the recommended velocity of the refrigerant flowing through this suction line is 750 feet per minute, or FPM. Additionally, we're given the density of R410A refrigerant as suction conditions, which is 3.56 pounds per cubic foot. With all this information, our technician now needs to determine the required mass flow rate of the refrigerant, which will be measured in pounds per hour, or lb/hr, in order to ensure proper system performance. This is a practical example of how understanding system components and flow characteristics is very critical within the HVAC world in order to design and maintain efficiency and reliability. Continuing with question 1, let's walk through the solution process. First, we have the velocity, which is 750 feet per minute, or FPM, and the density of R410A at suction conditions is 3.56 pounds and cubic feet. The formula we'll use in order to calculate the mass flow rate is mass flow rate pounds/hour equals velocity FPM times cross-sectional area, which is squared feet, times density, which is pounds and cubic feet times 60. The length of the suction line is given as 50 feet, but it is not directly needed for this calculation. We also need to find the cross-sectional area of the suction line, which depends on the diameter. Within this case, the suction line diameter is actually 2 inches, which we convert to feet. The cross-sectional area works out to be 0.0218 squared feet. Now, we can plug these values within the formula. That will be mass flow rate equals 750 times the 0.0218 times the 3.56 times the 60. And that would equal to 3,493.2 pounds/hour. So the required mass flow rate of the refrigerant is actually 3,493.2 pounds/hour. And that will be the answer for this word problem. Now, looking at our second word problem, this time focusing on the duct sizing for an HVAC system, a contractor needs to install a duct system that delivers 1,200 CFM. That is actually cubic feet per minute of airflow. The duct run includes a 30-foot straight section and also a 290-degree elbow. We're given a friction loss rate of 0.08 inches of water column per 100 feet of ductwork. But in order to maintain system efficiency, the maximum allowable pressure drop is only 0.1 inches of water column. The challenge here is to determine the correct duct diameter that will allow the system to deliver the required airflow while keeping the pressure drop within that 0.1 limit inch. This is a common scenario within the field where airflow, friction, and also duct sizing must all be balanced in order to ensure the proper system performance. Let's walk through the solution for this duct sizing problem. We're given the required airflow of 1,200 CFM, a duct length of 30 feet, and also two 90-degree elbows. The system allows a maximum pressure drop of 0.1 inches of water column, and the friction loss is 0.08 inches per 100 feet of duct. In order to start, we come to calculate the total effective duct length. The elbows add extra resistance, and in this case, they account for an equivalent length of 60 feet, 30 feet each, bringing the total length to exactly 90 feet. Next, we calculate the total friction loss using the formula. With that formula, it will be total friction loss equals F/100 times the length. Now, substituting the values, those being 0.08/100 times 90 would come to equal 0.072 inches of water column. Since this is still under the 0.1 inch maximum, that means that we are still within the limits. Now, using duct sizing charts or software that relate to airflow, pressure drop, and or friction loss, we come to find out that in order to deliver 1,200 CFM with that 0.072 inches of pressure loss, the required duct diameter will be 12 inches. So, to answer this question, The final answer would be the duct size should be a 12-inch diameter in order to meet both the airflow and the pressure drop requirements. That being said, that brings us to the end of my presentation. If you have any questions or would like to go over any topic that I have covered, please feel free to reach out to me so that I can happily discuss them with you. Thank you so much for tuning into my career project. This presentation was made by me and I am truly thankful.